Okay, you guys, a whole bunch of questions were asked on homework on section 2.1, so I kind of thought I'd make a notebook file here and try to knock a few of them out at once. So this might be kind of a long video. Feel free to just go ahead and fast forward and get to the problems that you wanted to see. So the first one it looked like that I was asked numerically here was number 15, which gave you a function here, f of x is equal to e to the x. And if I remember my directions right, let me go back and look at them again. They were asking us to estimate the instantaneous rate of change at the point that's indicated. So for us here, that would be at x equals 0. So, just to make sure that everybody understands the big idea of this section, we are not actually equipped just yet, you guys, to find, for real, an instantaneous rate of change. But what we're doing instead is using an average rate of change over a really small interval to estimate what that instantaneous rate of change might be. So, what I've drawn here on the side is the graph of f of x is equal to e to the x, which hopefully we know well. And if we're interested in the instantaneous rate of change at the spot right here where x is equal to 0, then what we had talked about here is the difference between two fundamental concepts when we're talking about rates of change. Now, prior to this, we had been just fine at coming up with average rates of change. But the important thing to understand is that an average rate of change requires two data points here. So we would start this interval maybe at x is equal to a, and we would end it maybe right here at x equals b, and we would draw the one and only line that's created by those two data points. And that is what we call a secant line. And the way we came up with the slope of a secant was simply doing the formula for average rate of change. In fact, let's go ahead and write that down, that the formula for a rock is the same as the formula for slope of a secant, which was going to be change in y, so f of b minus f of a, all over the change in x, which is b minus a. And then the big idea that we talked about in our notes in 2.1 is the idea that your average rate of change will become more like an instantaneous rate of change as the width of this interval right here, b minus a, approaches 0. We can't ever let it equal 0, but we can let it approach 0. So to estimate the instantaneous rate of change, we might do the same formula we did up above right there for average rate of change, but let me go ahead and specify a really small interval that exists somewhere right around this particular value here, where x is equal to 0. So I think probably the best way to do that, and I think I went through this in our notes, is to maybe go 1,000th to the left of 0, which would be negative 0.001, and then 1,000th of a unit to the right of that, 0.001, but positive now. And if we did that, this is going to give us a very small interval right here on which we'd be able to determine that instantaneous rate of change. So since I'm going to be doing this, I think, on a lot of the problems that you guys asked me about, let me go back to my calculator file here, and I'm going to open up a new document here, just starting from scratch. Although if you remember, I recommended for you guys here that you not redo all of your work here, and that rather you just keep one document open for really most of the chapter, to be honest. So what I'm going to do here is I'm going to define a couple of functions. I'm going to hit, this is my menu button, guys, and then for you it's going to be one for actions and one for define. And I'm going to go ahead and define, let's see, what we call the function. I think in notes we did AV, and then I think in parentheses we had two input values, and I can't remember exactly what we called them in the notes. I'm going to call them A and B here. So the average velocity defined from A to B, all right, is going to be equal to, and here we go. Now I'm going to reference a function I haven't defined yet, which is kind of a bad idea, but I think we'll be okay as long as we define it before we actually try to use this function. So I'm going to define this just like the formula we wrote down just a second ago, and get f of b, that's how you do that, minus, again, there was the f was back over here. Gotcha. Here we go. Minus f of, I forgot to close my parenthesis there, shoot. Okay, there we go. So f of b, sorry guys, bear with me here, and then minus, here we go, back here, f of We'll go with A, sure. Okay, so f of b minus f of a, hit my down arrow now, and now I will go with b minus a down there for the denominator. Okay, and there's our average value function defined. But that's only going to work if we actually define what the f function of the numerator is. So once more, I'm going to hit menu 1 and 1, all right? And we're going to define that numerator function, which is going to be, here we go, f, and for this one right here, we really just need one variable in there. I guess I can go ahead and call that f of x. Doesn't really matter what variable we put inside there. And f of x was equal to, nope, forgot a parenthesis there again. Okay, so f of x is equal to, and we'll go with e to the x power. That's unique to this particular problem now. And now from there, we're going to go ahead and we are going to evaluate that f of x function that we went ahead and typed into our calculator already. So to do that, we are going to, let's see, it was called AV, so I'm going to go to my keyboard right here and type in AV, and you'll notice it just got bold, indicating that it knows what we're talking about. And now we're going to put in the interval that we had discussed for this problem, negative 0.001, comma, and then ending at positive 0.001. So what we are finding here, everybody, is an average velocity. However, we're doing this on such a small interval that this average velocity is going to serve as a very good approximation for the instantaneous velocity. And when we do that, boy, it sure looks like we get something very, very, very close to 1. And so we would round to 3 decimal places, and we would go ahead and write our answer then down that average rate of change, which approximates our instantaneous rate of change, would be 1.000, and we do need all those zeros at the end, everybody, to show that we've actually rounded here. Now, a little bit later on in this chapter, or maybe even early into chapter 3, it's going to seem silly that we did that in such a detailed manner, because there certainly is a much faster and more efficient way of doing it, but that's all we've got for right now. And so what we've really done right there, guys, is instead of drawing a secant line through 2 points on a curve, we really drew a tangent line through that 1 point on a curve, and that is roughly the slope of that tangent line that we just came up with, right about 1. Now, I drew that graph by hand, so I'm really not that concerned about the fact that that red line that I drew seems to have a slope that's less than 1, but that's good enough for now. Okay? All right, so that was number 15. So again, if we're struggling with these problems a little bit, I think we need to understand this concept here, that we are finding an average rate of change, but we're letting that approximate an instantaneous rate of change by just taking an interval here that's really, really, really small. Okay, next question we were asked was about problem number 19. They give you a function here talking about the height of a small mass oscillating at the end of a spring. Okay, so we've got something that's hung here, and there's a spring coming down, and then there's some kind of weight, at the bottom, which we usually typically draw looking like a trapezoid, something like that. And that thing is bouncing up and down now. And the height of this spring is given to us by this function right over here, 8 cosine of 12 pi t. Okay, so with all that in mind, they've asked you, this is weird, they gave you an A and a B, but A is really asking you for 2 different things, and I'm really not sure what they were getting at by asking you one very tight interval and then one much wider interval and not really close to each other at all. But okay, I can answer their question, I think. Okay, so the first average rate of change on the interval from 0 to 0.1. All right, well, to do this, we are already set up with this function in our calculator here. You just saw me do the AV function that I wrote on problem number 15. The only thing that's going to change is that the f of x function that we typed into our calculator that was unique to number 15 is going to have to get replaced with this function right here. The other tricky thing is the fact that this is a trigonometric function, and we want to make sure, unless the directions ever tell us specifically otherwise, we want to make sure that our calculator is in radians and not degrees when we go to type this one in. Okay, so I'm going to switch back to my calculator over here. I'm not going to redefine the AV function, but Since the AV function references the f of x function, we need to redefine f of x. So menu 1 and 1, and we are now just going to write over what we had there before. So this is going to be to redefine f. Let's go back to here now. All right, so f of x to equal, and instead of typing this in with a t, we're going to go ahead and put an x in there. By the way, real quick, on my calculator, way over here on the left-hand side near the top, you guys can see home 1.1, and then below that, it tells me that I'm in radians. If your calculator up at the top says DEG for degrees, you're going to have to hit the home button, go to your settings, your document settings, and then change those degrees into radians. And then at that point, you should probably hit make default. Okay, so my function here was going to be 8 times the cosine of, and we had a 12, and there's a pi button right there, and their function has a t. We're going to go ahead and put an x right there, since we define this as f of x, not f of t. So now that is done, the AV function that we defined a while ago should now work for this particular problem. So let's go ahead and evaluate the AV function, and we are doing this on an interval here starting at 0, comma, and ending at 0.1. And the calculator is going to do all of this work for us, guys, and we're going to get negative 144.721. Negative 144.721. And guys, we're going to do this enough. I'm going to be comfortable with you guys not showing me the work on there other than what I'm writing here on the left. And now we're going to do it again from 3 to 3.5. So this should go even faster now. I'm just going to hit up, up twice, hit enter for copy and paste, and let's get rid of those A and B values, and let's replace them with 3 and 3.5. Okay, oh, and here we get 0. There's probably a reason they asked us for that, so that is 0 right there. And that's all that it asked us to do on part A. And then B, estimate the instantaneous velocity at t equals 3. Well, again, let's try to write this out. The instantaneous velocity, and I just realized, guys, I wrote average rate of change. That's not wrong, but it'd probably be better to write average velocity right there in both of those cases. And now we're doing an instantaneous velocity at the time when t is equal to 3. Well, the way we are going to approximate that instantaneous velocity is by finding an average velocity on a really small interval that contains or is right around t equals 3. So I'll do my same trick again. I hate to be boring and predictable, but I'm going to go 1/1000th less than 3 to 1/1000th greater than 3. Okay, so it's the same h of t function. So again, we're all set. Just going back to the calculator, and once more I'm going to hit up, up, and I'm going to copy and paste that formula here. And let's see, instead of starting at a 3, we were now at 2.999. And instead of ending at 3, we're at 3.001. Okay, and let's hit enter. Interesting. That gives us 5 times 10 to the negative 10th power. So I don't know how long it's been since you guys have seen scientific notation, but anytime you get something in scientific notation with a negative exponent, that is basically your calculator saying that the answer is 0. This is actually what, guys? A decimal point followed by 9 zeros and then a 5. So it's not exactly 0, but when we round it to 3 decimal places, we do end up with a whole bunch of zeros. So I'm going to go ahead and write that answer of 0.000, and that's what I would put right there, everybody, for estimating that instantaneous velocity at t equals 3. Okay, so that takes us through number 19. Let's look at number 23. This was a weird one. One thing I don't think we've talked about yet, guys, anytime you see this GU logo at the beginning of a problem, that stands for graphing utility. It basically means this is a calculator problem, and you can use the calculator to do most of the hard work for you. It's not one you should be able to do by hand. So an advertising campaign boosted sales of crunchy crust frozen pizza to a peak level of S0 dollars per month. So S naught is some dollar amount then that we were making here in terms of sales. Okay, a marketing study showed that after T months, monthly sales declined, that's important to note, into this formula right over here. So S of T, let's write this out here, guys, so that S of T is given to us by S naught, which I believe is going to be a constant, multiplied by some function, G of T. And G of T was given by this amount right over here. Okay, that's interesting. And then the question asks, do sales decline more slowly or more rapidly as time increases? Answer by referring to a sketch of the graph of G together with several tangent lines. Okay, so they're kind of giving you a formula here, a roadmap for how it is that we're going to try to figure that out. So what's going to happen here, guys, is we're going to go ahead and again, not knowing what S of T is, I don't think it matters too much here, but we're going to multiply some constant times this G of T function. Okay, so let's see what that might look like. Yeah, I don't think there's any way to know what S naught is, so I might just pick a value and then see what happens there. So I'm going to go to my calculator here. I'm going to add a graph page, everybody. So I'm going to hit add and add a graph page. And the function we're going to deal with, I'm going to go ahead and put in 100 right now. It seems like a nice simple number here to put for S naught. And then we're going to multiply that by this G of T function. And the G of T function in problem number 23 was given to us by a stacked fraction of 1 over, and then we had a square root of 1 plus t, or I'm going to have to put a 1 plus x right there since that's the variable we are using in this function. Now, if you can't see anything, that doesn't surprise me. We probably just need to scale out on this graph a little bit. Okay, and we see something like this. Okay, so it looks pretty simple now that I look at it here, guys. It certainly looks like that in this particular case, we basically just have the top right corner of a hyperbola. My guess would be, and I think we can verify this numerically, that whatever value I chose for S naught, which for me was 100, I think that's the y-intercept of this graph. I could think about that. The y-intercept occurs when x is 0. And when x is 0, we're going to take the square root of 1 plus 0 on the bottom, which is 1. 1 over 1 is 1, times 100 is 100. So yeah, that's what this one looks like. Okay, so let me go ahead and draw that graph really quickly on my paper here, guys. We have a y-intercept right here that's equal to the value of S naught. And then it looks like this graph is going to do something like this. And given the fact that it looks like this thing has a horizontal asymptote here at the x-axis, that implies that our sales are never going to completely drop to 0, but they're certainly going to approach 0. So that's what I think they really wanted us to do here. But now if I go back and read the question again, do sales decline more slowly or more rapidly as time increases? So what they're asking us to do is consider the instantaneous rate of change of this function, or the slope of the tangent. And I'm going to do that at about 3 different points on that curve. So just kind of eyeballing, I think our tangent line right here would look something like that. You'll notice that it has a negative slope. We'll talk about this a lot in Chapter 3, but anytime your function has a negative slope, or your tangent line has a negative slope, it means that your function is decreasing. Now that line has a very negative slope, which means that our sales are decreasing very rapidly. But as time goes on, my tangent line is still going to have a negative slope. Our sales are still falling, but they're not falling at quite the dramatic rate that they were early on. And then the last one that I'm going to draw is going to be over here somewhere. And once again, the slope of that tangent is negative, which indicates then that our function is still decreasing, but it's not decreasing very quickly. So back to the question, do sales decline more slowly or more rapidly as time increases? I think we would have to say here that sales are going to decline more slowly as time increases, but we can see that by looking at what happens to the slopes of our tangent lines. Okay, So that's number 23. Okay, 27. The only question I was asked here, guys, was about part D. So I'm going to go ahead and just deal with that. And if anybody else wants to see other parts of this worked out, you guys go ahead and let me know. But this question here asked us to draw the tangent line at t equals 40 and estimate its slope. And to do this, everybody, you really have to do a good job and you have to get the graph exactly right. So this doesn't work real well if you're trying to just graph this on your paper. At t equals 40, we are looking at this point right over here on the curve, and they want us to draw the tangent line. Now, there's nothing to this other than to eyeball it, you guys. But if we do that, all right, let's see. I think that tangent line is maybe going to look something like this. So that's just a guess. But now for the second part, estimate its slope. This is where things get a little bit interesting. If we're going to try to estimate the slope of our tangent line, what we are going to need, everybody, is 2 points located along that curve so that we can try to figure out the slope between them. Well, I definitely would want to use this point right here, which is the point of tangency. That happens when t is 40. And it kind of looks there like f of t is going to be about halfway between 80 and 100. So I'm going to say that that point is 40, 90. Now that's a guess. I don't know for certain that that's what that ordered pair is, but that's the best I can do here looking at that graph. The other thing now, and they usually are pretty good about making this work out for you, you've got to find another clean point that's located on that blue tangent line. And when I say clean point, I don't mean this, because that one I'm just totally guessing what the coordinates are. But I do see one point that looks pretty clean right about there, guys. And that ordered pair there looks like it's 20 and then a y value here of 80. So now we've got two ordered pairs that are located along that tangent line. We should be able to estimate the slope there. So change in y, I'm going to go 90 minus 80 up in the numerator. And on the bottom, change in x, or actually change in t, is going to be 40 minus 20. So that is going to get us a 10 over 20, and last I checked, I would say the slope of that tangent is approximately equal to 1/2. Okay, so that's number 27. Now, I should be clear here, guys, and actually I'm looking at the answer right now in the book. They don't have it as 1/2. They have it as 0.55% per day. And you'll notice that 0.55 is really, really close to 1/2, but it's not quite right. I wouldn't be able, though, if I were looking for that answer of 0.55, I wouldn't be able to tell you guys that you're wrong because we were all just guessing at the coordinates of those points. So as long as you made clear to me what 2 points you thought were on that line and that you were using, as long as those 2 points correlate to this slope here that you came up with, I'm going to give you guys full credit for whatever answer you come up with, as long as the 2 points that you used are reasonable guesses for what was located on that line. But there's not going to be just one right answer to these problems where they ask you to estimate. And let's take a look at number 31 lastly here, guys. I think that's the last one you guys had asked me about, up until this point anyway. Okay, so in 31, they're asking you now which graph in figure 17, A or B, has the following property. For all x, the average rate of change over the interval from 0 to x is greater than the instantaneous rate of change at x. And we're supposed to explain. Okay, here's the first thing we should know, everybody, and if we don't have these ideas down, we better get them down soon. That average rate of change is synonymous with the slope of a secant line. So they're asking us to compare the average rate of change over the interval from 0 to x. So that's a secant line that starts here when x is 0, and it ends here with an x coordinate of x, which is kind of stupid. But anyway, so I'm going to go ahead and draw the secant line right there. Okay, gotcha. And that is where we are at there. Then in the second one, we're looking again at a secant line right here, starting at 0, ending at some random value x, and we're going to draw the secant that goes through those 2 points as well. Now, let me switch to red, as I normally try to do, and the next thing they're trying to get us to do is to compare that average rate of change to the instantaneous rate of change at x. An instantaneous rate of change is the same concept as the slope of a tangent. But it's not just the slope of a tangent anywhere, it's the slope of a tangent at x. And x is what we used for the right endpoint of both of those average rates of change. So I'm going to try to draw the one and only tangent line to these curves at that spot right there. And just eyeballing here, but my tangent line in the first graph might look something like that. And my tangent line in the second, not very well drawn, might look something like that. So let's take a look and let's read this question again, because I've kind of already forgotten what they were asking us. Which graph in figure 17 has the properties that says, for all x, the average rate of change over 0 to x, so the average rate of change, is greater than the instantaneous rate of change. We want average rate of change to be greater than the instantaneous rate of change. Well, if we use these two ideas right here, average rate of change is the same as slope of a secant, and we want that to be greater than the slope of our tangent, which is the same as the instantaneous rate of change. So which of those two graphs, A or B, has a secant line in green that has a greater slope than your tangent line in red? And the answer to that is only graph B. In graph A, the tangent line is actually steeper than the secant line, which means that the slope of the tangent would actually be greater than the slope of the secant. But in B, the secant in green has a greater slope than the tangent in red, so B is going to be the one and only answer here to problem number 31. Okay, guys, let's keep those questions coming if you have more, but hopefully that pushes you guys in the right direction.